Yeah. Yeah. This meeting is being recorded. Excellent. And I reiterate, please, I'm happy to answer questions. It very much helps with these Zoom calls, just to, again, know that people are actually out there. So yeah, so it's an interesting format, and so I'm going to sort of make this somewhat biographical, and then sort of stop halfway through to get into some of the science. So let's see. So, oh, one sec. There we go. There we go. So I was born there in London, but when I was quite young, the family moved up to where the arrow goes to, which is rural Lincolnshire. It's kind of sort of middle of nowhere, about as middle of nowhere as you can get in England. So that dot in the center, that's the family house, and as you can see, it's surrounded by fields and woods. The rather small village is down to the left, which was a good walk away. And then my high school was about 6 miles west of here, across the fields. And the nearest thing approaching a city was another 20 or 30 miles beyond that. So in many ways, quite an idyllic childhood out of the middle of nowhere. My family was actually quite scientifically orientated. My mother trained as a biologist, and she taught at the College of Higher Education. So that's sort of the last couple of years of high school and going through college, undergraduate level. And my father ran the local Nature Conservancy trust. So they took care of all the wildlife preserves in the county. So, you know, childhood was dissecting sheep's eyes and sheep's hearts on the kitchen table with my mother, chemistry experiments in the kitchen, walks across the fields with my dad, trying to explain the birds and the flowers, and improvised explosives in the fields to an extent that would got me into a lot of trouble, I think, in the modern era. So apart from just the sort of science, biology, I mean, with my mother, you know, if she was gutting a fish, that would turn into a anatomy lesson. But the other thing she did when I was quite young, over the summer break, she snuck home one of the computers from the college. And so this was my first computer, was a PET, Commodore PET. It wasn't mine, but I got to play with it for a whole summer when I was about 10. So that's sort of my early passion there is computers, really. Computers and chemistry. Yeah, so I had this Commodore PET, and then I had a Sinclair ZX81, and I've been coding ever since. However, despite, you know, quite a science-heavy family upbringing, high school was not so great. It wasn't that easy. So this is my high school in the town of Horncastle, about 6 miles away. And on reflection, although one doesn't necessarily appreciate these things when one's a child, I think it was actually a pretty good school. They had some very good teachers, and it was kind of a science-focused school. So we started secondary school at 11, and we had separate classes for physics and biology and chemistry. However, I'm somewhat dyslexic, and so my reading and writing ability was years behind my peers at this point. And so the net upshot was that my academic performance was very barbell shaped. I aced my math and my physics and my chemistry, no problem. And then I was absolutely lost in the class in English and French and foreign languages, and any class that required a significant amount of writing, like history, I just did terribly in. So that made the whole early high school experience very, very tough. Fortunately, in England, we specialize. And so by the end of high school, by the last year, I was only taking math and physics and chemistry, and it was a breeze. In fact, really, they could have pushed me much harder. It became trivially easy. Now, as I said, I had some very good teachers. I remember, for example, Mr. Bainbridge, who was my math teacher. But I also very much remember my first chemistry teacher, who was very influential. And he was Mr. Heward, and he had a kind of a Rick affect. He kind of looked like Rick from Rick and Morty. So, you know, crazy hair, lab coat, stains all down the lab coat. And he would blow up the chemistry lab during demonstrations on more than one occasion. He would switch on a Bunsen burner for a demonstration. He would turn the gas full on, and then he would go looking for his matches. He'd look at the drawer, he'd pat his pockets, he'd look around, he'd find one, it was empty, he'd find another one, he would try to light a match, he'd finally get a match lit and woof, and you know, he singes his eyebrows. And this again was just a regular occurrence. And so I was completely hooked. I love chemistry. I did a lot of chemistry on, like I said, at the tabletop with whatever chemicals I could get hold of at home, which was nothing particularly serious, but a lot of electrochemistry too. That was a lot of fun. And so, again, in England, we kind of specialize kind of early, and you have to make a decision about what major you're going to have when you go to college quite early. And so I picked chemistry because I was very much enjoying chemistry. It turned out to be, although I've drifted more towards physics over the years, a good choice for various reasons. Chemistry is often called like the central science. It sits between biology and physics and other things. Now, the alternative would have been, I think, computer science, but my school didn't really emphasize the computers at that time. I think there was a computer class, but I think it conflicted with physics or something, and the physics was considered a more important class. So computers always my other passion. So then undergraduate, I go to the University of East Anglia in Norwich, and this is the campus at the top. You could tell this campus was built in the 60s because of the concrete brutalism. There's this long, can you see my cursor? Anyway, there's this long wall of building at the back, and in the middle somewhere was the chemistry department. These ziggurats in the foreground are dorms, which were quite nice. They had nice views. I didn't, unfortunately, get to stay in those. I stayed in the crappy dorms. And this building way on the far left is, in fact, the Avengers facility. It's actually featured in a couple of the films, got blown up at the end of Endgame. So where was I going with this? Oh, so UEA had a trick. The chemistry department had a trick for attracting talented students, and that was that they offered an exchange program where you got to spend your middle year off in a foreign land. And this was extremely appealing to me. And so I signed up. And so I spent my second year of college at UMass Amherst in central Massachusetts, which was great. I really enjoyed it. It was very cold and then very hot. As those of you in Boston, I no doubt understand the weather over there, but coming from England, I did not. I froze and then I sweated, but I loved it. I can't say I actually got a lot of work done when I was there, but I did enjoy myself very much. Now, while I was here at UEA as an undergraduate, what I thought I wanted to do was synthetic organic chemistry. And as an undergraduate, I did essentially no theory, the bare minimum amount of quantum mechanics, no math. I took some computer science classes because it was fun. But apart from that, again, you tend to be very specialized. It was just organic chemistry. And I really liked it up until the last year. In the last year, they put you into an actual lab. And I spent a semester trying to do synthetic organometallic chemistry. Organometallics are air sensitive. You look at them wrong, they'll turn into a brown sludge. And I had a terrible time. And it turns out I'm a really bad synthetic organic chemist. Being an experimentalist, being a synthetic chemist, it requires you know, a special magic touch, an attention to detail, being in the moment. Well, none of these are my strong points. So this turned into a bit of a problem. I did a 1 year master's at UEA in biochemistry. I did enzyme kinetics. So still on the experimental side. And then I applied to the States to come, because I wanted to come back to the States for grad school. And I only did the master's at UEA because I missed all the deadlines for getting into grad school in the States. I had no idea they were so early, that you had to take the GRE so early. So I just walked downstairs and signed up for the 1 year master's program. So I had an extra time to go apply for grad school. So I ended up at Boston University. I was not actually there very long because this was the point where I just realized I actually wanted to do theory. So I still thought I wanted to be an experimentalist at this point. I was thinking about protein crystallography, but I took 2 theory classes. One was from David Coker on quantum chemistry. So what happened was BU had just installed a supercomputer, a thinking machine CM5, a beautiful computer for the time period. And I so wanted to play on this computer. And what they did was they organized access to that computer via classes. Each department had a class, and that class gave you access to the supercomputer. And in chemistry, that class was quantum. So I took David Coker's quantum class so that I could play on the big supercomputer with the blinking lights, which was beautiful. But then I discovered I actually quite like quantum. And this was quite hard because, like I said, I'd done next to no math, next to no quantum. So it was a lot of catch up. And the other was from by Yam. He taught a class on complex systems where he taught a lot of basics of statistical physics. And through him, I met Gene Stanley, who's over there at BU. And he introduced me to the Green Book, The Introduction to Modern Statistical Mechanics. This is a classic book. And I loved it. And I discovered this is what I really like: statistical mechanics, thermodynamics. And it's this interplay between the physics and the information and the computation. At the very heart of thermodynamics is really the physics of information. It's that interplay between energy and entropy. So I decided that's what I wanted to do. So I presume some of you guys are thinking about going to grad school. The most important decision you have to make is what you're going to study. You have to find something that, 1, you're good at, and 2, that you're passionate about. There's no point trying to slog through a PhD if you're not passionate about what you're doing. Then the next most important decision is who you're going to work for. And then the university is like the third choice. I mean, a good university is a good thing. It gives you more flexibility if you do want to change fields. But really, who you want to work for is the most important thing. So I wanted to work for David. David was a great statistical mechanic, great scientist, really tough. Came off a bit of an asshole at times. Just social skills had no filter. And he tended to treat his students not so well. He burnt out a lot of students. And about 1 in 2 students didn't make it for his group. Some left the group, went to different groups. Some left science altogether, and some he outright fired. But once you proved yourself to him, which took a while, then he was great. He was great as an advisor. And the period I was in his group, there was a lot of great people. I think in the time period I was in the group, something like 6 are now tenured professors. So I applied, I dropped out of BU. As I said, I actually worked at the Coop for a while and at a bookstore in Copley Place. I reapplied to grad school. I got into various places, but fortunately I got into Berkeley and went to the chemistry department there. So this is where chemistry actually becomes helpful. In the United States, a lot of statistical physics, statistical mechanics, thermodynamics is in chemistry departments. So over the years, I still sometimes call myself a chemist, but I've much more drifted towards physics. But the chemistry lets me have that flexibility. So I went to work for David. He sort of grudgingly let me into his group. Fortunately, my first project was on the structured liquids, which is something David quite liked. So I got a paper out relatively quickly. He was quite happy. And then something very fateful happened. So Chris Jasinski wrote this paper, which is now very famous. And he came up with this result, which is now called the Jasinski equality. So if you look at the dates, you see this paper was received 1 year and not published for something like a full year later. And what happened was nobody believed it. I'm told by one of the editors that one reviewer said it was wrong, another said it was trivial, and the third said he'd already done it. I believe the reviewer said it was wrong was David Chandler, and he wrote to Chris to explain to him why he was wrong. And Chris, in an amazing feat of diplomacy, wrote back to David and convinced him to reconsider his position. So David invited Chris to Berkeley to come give a presentation to the group about this idea he'd had. So this is a very fateful talk, and I missed it. I had my qualifying exam like the next day, and I was a bit preoccupied. But Chris left behind a preprint and a generally good impression, and I consumed it. I became obsessed with it. And the reason is that the result he came up with, I just spent like the last year solidly learning the foundations of thermodynamics and system mechanics. And the result he came up with looked kind of impossible from what we thought we understood. So let me try, this is a bit of the physics here. Let's go back in history a bit. The second law of thermodynamics is the absolute foundation of thermodynamics and statistical mechanics. It goes all the way back to 1865, the Clausius inequality. Clausius realizes that it is this quantity energy that is conserved. And that was figuring that out was a big deal. It took a lot of work. But he realized there's this other quantity, which he named entropy to sound similar but contrast to energy, which increases. And he said, actually, entropy of a spontaneous change always goes up. And if we're in equilibrium, thermodynamic equilibrium, it stays the same. And so in the future, entropy is going up. Turns out there's actually an even stronger statement than that. It's not that the entropy goes up in the direction of time we call the future. It's that the future is the direction of time in which entropy increases. The fundamental laws of physics are all time reversal symmetric. The only thing that distinguishes past from the future is the entropy increase. But if we're looking at very small systems, it's not entirely true that the entropy always goes up. So here's an example. Suppose I'm compressing a gas in a piston, but I actually have very few particles in the piston. Let's say there's 4 particles. Then every time I compress the piston, I do a different amount of work on the system. The work, as energy goes into the particles, it eventually goes into the heat bath, that increases the energy of the environment, increases the entropy. So the higher the work, the bigger the increase in entropy. But sometimes you can have these random fluctuations where all the particles move out of the way just before I push the piston in. I end up not having to put any force on the piston at all. And that's those, if you look at this distribution of works, the far left tail actually represents realizations of this process where the total entropy of the universe went down. Now, what Chris did was that this is not really a contradiction. We just have to take the statistics into account. The right way of stating Clausius inequality, a more complete way of stating it, is the entropy always increases on average. If I averaged over many repetitions of that process, the entropy will go up. And if you look back in history, you look at like the founders of system mechanics, people like Maxwell and Boltzmann and Gibbs, they absolutely understood that the second law was a statistical statement. They had it wasn't always true. It had some probabilistic point into it. But I don't think they knew exactly the right way of stating it. Chris made this clear. The right way of stating it is, on average, the entropy goes up. And what he did was he rewrote the second law. He took the entropy change and put it up into the exponential. So now it's an exponential average. And we turned what was an inequality into an equality. And this relation is now true irrespective of how hard I'm pushing that piston, how far I push the system out of equilibrium. And that's what seemed impossible. We understood a lot about equilibrium statistical mechanics, but the fundamental things we could say about a system that's out of equilibrium are very limited, whereas this is a very fundamental relation which applies out of equilibrium. So I got like just obsessed about this. I was emailing Chris. I hadn't met him. I didn't meet him for several years, but we were emailing each other back and forth a lot during this time period, knocking ideas off each other. We're the only 2 people working on this. And eventually I came up with a deeper perspective of why the Jasinski equality is true. And this is my notes from when I was sitting at a coffee shop and finally figured it out. You can see the ta-da down at the bottom.
Crooks?
Yes.
Could you go back 2 slides?
2 slides.
That's it, exactly. So how do you go from the right-hand side to the left-hand side? Like, how
Um,
does...
that's actually a single step. It's called the Jensen Inequality. So it's a standard inequality that you pick up. It comes up all over the place in math and physics, in information theory. So it's just the fact that if you have any function that is concave, and you take the average is always going to be above the line. If you take a convex average, it's below the line. And that's all it is. So going from the right-hand side to the left-hand side is a single line of math. Going from the left-hand side to the right-hand side took over 100 years of hard work from generations of physicists. And all we did was, in the end, was slightly rearrange the equation, which is just one of those amazing things. And I'll try to explain why this relation wasn't spotted for so long. Does that answer the question? Good. So the deeper symmetry is on the trajectories themselves. So if we look at any system and we think about the trajectories of the particles, well, there's a time reversed trajectory. So there's some trajectory as I'm compressing the system. There's a time reversed trajectory. The particles follow the same trajectory in reverse as I expand the system. And there's a symmetry in the probability of observing those two trajectories. And that symmetry is exactly given by the exponential of the dissipation, by the exponential of the change in entropy. So entropy doesn't just dictate the direction of time, that if entropy is increasing, time is in that direction. It's a quantitative breaking of the time reversal symmetry on the level of trajectories. Now, I had been hiding from David Chandler for a couple of months at this point because I was working solidly on this, and I'd meant to be working on something completely different. I don't remember what it was. And eventually he nailed me. He caught me in the lab on an evening, and he nailed me to a whiteboard and said, "Tell me what you've been working on." And so I explained this idea about where the Jasinski equality was coming from. And when I finished, he looked at me and he said, "That's really good," which is like, I think it wasn't even as high praise as that, but that was the essence. That didn't suck. And that indeed, and you should write this up. And I didn't have anything to do with this, so you should write this up on your own. That was like the best thing he ever did for me. So I wrote this single author paper on this subject, which ended up being very highly cited. Which was also a huge, I remember I'm a little dyslexic, so writing papers is a slog. Even now, I can't just write a paper. I have to craft it carefully, laboriously. But eventually I managed to get this paper written. And then, yes.
I think Mitchell has a question.
Oh, Mitchell.
Oh yeah, Dr. Crooks. I have a question. 3 slides ago. Sorry, I should have.
Yeah. No. This one? Or this one?
Yeah, this one. Yeah. So here, like delta S total has the unit of the joule per Kelvin. So I just wonder.
No, it has no. It has units of nats. So the joules per Kelvin, chemistry people use joules per Kelvin, and that's a totally artificial unit of entropy, and you should never, ever, ever use it. Entropy has natural units. If you're using natural logarithms, it's nats. If you're using binary logarithms, it's bits. There's absolutely... But okay, so the problem is, right, you've got energy, you've got entropy, and you've got temperature. And their units are related. So people define unit of temperature as joules, and then temperature is Kelvin. So, entropy has to be joules per Kelvin per nat, and nobody ever states the nat. Instead, we should take the entropy as being the fundamental unit because that has natural units. And Kelvin, obviously we use Kelvin, Celsius, what in real life, but when you're doing science, we just use nats or bits.
Oh, so here, we just consider the information entropy instead of the thermodynamical entropy.
There's no difference. There's absolutely no difference between the two. So that, that's a long, interesting discussion we could get into. The only difference between so Shannon information entropy and the way it was entropy, that P log P form first turned up in Boltzmann's work, and then it's really prominent in a special case, and then Boltzmann really nailed it. And then, of course, Shannon comes along in the 40s, and from a very different perspective, information theory comes up with the same form. The difference between them, they are the same thing. They're both entropy. The only difference is where the probabilities are coming from. So it's the difference between a thermodynamic entropy and some sort of information entropy is where the probabilities are coming from. There's nothing fundamentally different between the entropies themselves. But like I said, this is one of those fun things that people like to debate. So it's, but from my perspective, that's the right way to think about it. So one of the other great things I did, okay, so here's a secret that I'll tell you if you're doing research. The easiest way to make progress and write a paper is to read widely and spot connections between different subfields. It feels like cheating, but it can be great. And so what happened here was I'd already, in the first paper I wrote, this relation, which is now called the Fluctuation Theorem, was implicit. I already knew it. It was in my notes. I just didn't write it down. But then I was looking through other people's work, and I finally made this connection to these other groups who would define this fluctuation theorem. They were coming from a very different perspective. But if you screwed your eyes up, you could see that it was really fundamentally the same relation. You know, I mean, with tweaks, again, they were coming from a different perspective, but you could see it as a unified thing. And so I wrote this paper, which I was very proud of, just simply because I had spotted the connection between Chris's work and this work from these other people in Europe and Australia. And so instead of thinking about it as being a symmetry on the trajectories, you average over trajectories and you think about a symmetry on the work distributions. And that's actually good. The problem is you can't experimentally verify the trajectory ones because I can't sample trajectories directly, but I can measure these work distributions. So, okay, I wanted to give you just, you know, why is the Jasinski relation, the fluctuation theorem true? It turns out to be trivial. It really depends on two things we already knew. So just, if you ever take a stat mech class, thermodynamic class, this first one is the one thing you should take away, is that at equilibrium, the probability distribution of any state is given by the Boltzmann distribution. So it's the exponential of the energy of the state divided by the temperature is the probability of that state. So this form first came up in Boltzmann's work, and again in a special case. This is why it's called Boltzmann distribution, and Gibbs really nailed this. So like we knew this by like 1905. The other is, again, an equilibrium system is fundamentally a system with no time. I can, you know, a glass of water is just sitting there, and even if I look at the microscopic trajectory, it looks the same statistically forward in time and backward in time. And this is called microscopic reversibility. It's just this idea that an equilibrium system is time reversal symmetric. And this was figured out in the 20s and 30s. And it goes even called microscopic reversibility or detailed balance, which is essentially the same thing. So it turns out that's really all you need to derive these results. Nobody figured, but it took all until Chris to really nail it. Why? And the reason is that people just weren't used to thinking about small systems. You look at a lot of stat mech papers, even up through the 70s and 80s, it's all about large macroscopic systems or large ensembles of systems. It wasn't really until the advent of computer simulations and the advent of single molecule, single atom experiments that people really started thinking about microscopically small systems in a thermodynamic sense. So that then was the end of my PhD. Unfortunately, I kind of burnt myself out. I worked like last 6 months in particular, getting papers out and writing up my thesis. I worked ridiculously long hours, 7 days a week, completely burnt myself out, couldn't face doing any more science. But it was the .com era. So I decamped and went and worked for a .com right in the middle of the boom. Then the .com crash happened, and the company I was working at called Donut.com, it was an early like e-commerce site, crashed and burned. But it was a lot of fun on the way down, and I got to do some proper software engineering, slinging Java code for the back end. So then I, you know, after the boom, the crash, you know, I sort of snuck back to the ivory tower and did a postdoc in bioinformatics, computational biology. In the meantime, something really interesting happened, and that was experiments, single molecule experiments came online, verifying these theoretical results Chris and I and other people had come up with. And that was a huge deal. I mean, previously, these results looked pretty neat, but it was very unclear how relevant to the real world they were. Maybe it was just some theoretical construct that didn't really apply in a practical sense. But no, these groups at Berkeley actually managed to do these single molecule experiments on RNA and verify the expected behavior. Jan was a postdoc at the time, I think, and was working on these experiments, and at some point realized that I was actually a postdoc at the other end of Berkeley and just phoned me up one day and said, we're working on this experiment. And I said, that's really cool. So that was a big deal. And that made the whole field really, reinvigorated my own interest into looking into these things. So I ended up at Lawrence Berkeley Lab for many years, running a research group. Had some very good students. Very proud of the work we did. I was originally a divisional fellow, then senior scientist, and have done a whole bunch of stuff in related fields of statistical thermodynamics. Again, sort of the thing that sort of ties my research together is this intersection between physics and information, between physics and computation. It's that boundary. So that intersection between where the physics, chemistry, biology, and information theory all sort of meet is the bit that I find has always attracted my attention. And then just to round up where I currently am, so decided I needed to change the scene. So I've decamped from LBL to go back into the startup world. Turns out quantum computing has got really cool again. So I got into quantum computing like a long time ago. But in a time period where it was very difficult to get research funding. So I could never talk anyone into paying me to actually do research on quantum computing. But now there are companies that are actually building quantum computers, and there's a lot of interest in trying to do practical algorithms on these machines. And again, it still ties into my central interest. It's that intersection between physics and information, which is very stark in the quantum computing world. So I worked at Rigetti Computing for a couple of years. I was at Google X last year. I'm currently consulting for a couple of startups. So yeah, startup world is fun. Those of you who are considering grad school or not, startups are great. They're a lot of fun. It's high risk, but a lot of energy to them. And you can do proper real research in these companies these days if you're in the right fields. Things like machine learning and quantum computing. So there's lots of really, really good research coming out of the companies. Also, if you go into grad school and you want to become a professor, that's great, but you should have a backup plan because that's a really hard path. So unless you're, I think you have a backup plan. And again, some people are really negative about industry, particularly if you go ask professors. A lot of them have never been out in the real world. But I think it's great. I think both are great. They have different pros and cons. So that's where I am now. That was sort of what I wanted to say. So I'll pass it back to any more questions. Or not. Timothy.
Hi, I'm sorry. I think I missed that slide, but I don't think you explained it in that much detail either.
No.
So why?
Yeah, I was trying to do a pretty high level. Which slide you?
Yeah. So why? So basically, the topic of this Chilloquium. Why is it that the physical laws are time reversal symmetry, but then the entropy keeps growing? Like, why is it? How is this paradox solved, basically?
So the first thing to realize is that why does entropy grow? Well, the intuitive idea is that entropy is some sort of measure of the disorder of the system, and things just get more disordered as you go along because there are more ways to be disordered than not disordered. The real sort of physics part of that is, why is entropy not already maximized? Why aren't we already at thermodynamic equilibrium? And the answer is because the entropy yesterday was lower than it is today. And before that, it was lower. And before that, it was lower. and you go all the way back, and eventually you end up with the Big Bang. So the whole arrow of time, in some sense, is coming from the fact that one direction of time, which we're relatively close to, the entropy was very, very low. And that, that sort of defines the whole arrow time. It's the fact that we start out low that allows it to increase at all. And so that, that then sort of doesn't solve the mystery. It just moves the mystery to, it's a cosmological issue. It's like, why on earth is what boundary condition of the universe that at one end, it's very low entropy. I'm trying to avoid saying the beginning, because the problem is you get into these, it's hard to talk about, because time, the direction of time itself is defined by the fact that entropy is increasing. So it's, when you're talking about the whole universe, it's a little tricky. It's only, the direction of time we call the past, because that's the direction of time where the entropy is low. So if you're not careful, you end up sort of going around in circles. Does that answer your question, or can we elaborate on that?
Yeah, I think
puzzled.
that's clear.
Yeah, but I mean, clear. But yeah, these are actually, when you get down to it, there's some very, very deep philosophical problems that still have not been entirely resolved to everyone's satisfaction. One of the tricks is it depends what model of physics you're using to describe your system. And one of the tricks I like to do is just to use a stochastic dynamics. So anytime you have a system and you're only looking at one part of it, but there's interacting with the rest of the world, the part you're looking at looks stochastic. And that makes a lot of the math much easier. Then I don't have to worry about deep questions about why the entropy is increasing. It's already built in. If you try to talk about an isolated system with deterministic dynamics, like Hamiltonian dynamics, then we get into some really interesting, deep philosophical issues about what does it mean to the entropy to be increasing. It's always comes down some level that you are hiding information or losing information in the correlations.
I have a question which I'm just kind of confused about something, I guess. But you're talking about entropy growing and everything, but you know that equilibrium is a maximum entropy state, right?
Mm-hmm.
I'm a little confused about where detailed balance. I don't understand if we're at equilibrium, near equilibrium, or what is the relation of these trajectories with respect to equilibrium, I guess.
So the trick is detailed balance, microscopic reversibility, is a property of equilibrium systems. So we can reason about equilibrium systems. The trick, though, is that a system, if I start beating on it, it doesn't know whether or not it's in equilibrium. Equilibrium isn't a property of the system itself, it's a property of the ensemble, of the whole probability distribution. So it means that even if I drive a system out of equilibrium, its behavior is still dictated that, if I left it alone, it still has to behave as if it was with the same symmetries as if it was in equilibrium. So that's where the trick is. So when you think about driving the system, so I drive it and I stop and wait a little bit. When I'm waiting, the system just does its normal behavior. It may be way out of equilibrium, which means it's in an improbable initial condition. But any state from an equilibrium system could be sampled from a non-equilibrium system. There's always the symmetry. It's just the probabilities are different, and that's the trick.
Is it something like in the Langevin equations? You have some relation between the diffusion constant and the damping, etc., like this Einstein relation?
Yeah, that's detailed balance. That's for the equilibrium system, and that's where that relationship between the damping constant and the noise comes in. That ensures you have this equilibrium detailed balance. Yes.
Okay, I see.
Yeah, and again, well, that comes down to, in the end, is the idea that the dynamics has to be statistically symmetric in time, so that if I look at some trajectory of the system, I sample and I look at some trajectory. Well, I sample and I could have sampled the time reverse trajectory. The probability of equilibrium of those two trajectories has to be the same. I can't distinguish forward in time and reverse time.
Have there
Jackson.
been any like applications of your interpretation of trajectories and how forward and reverse are like equally probable at like small micro levels?
Say that again. I missed the first part of the question.
Like, have there been any applications, not just verifications, I guess, of your theorem that you came up with?
Yeah. So one of the things is that in that relation in the Jensen inequality, for example, there's the free energy difference. And the free energy at equilibrium is like the most important quantity. It dictates all of the thermodynamics. So for example, if I want to know how strongly a drug binds to a protein, you measure that with a free energy change. So the net upshot, though, the practical upshot is that you can measure these free energies, which are equilibrium properties, from a non-equilibrium experiment. So you can do experiments which are very slow and stay in equilibrium, but thanks to Jasinski and related things, you can actually also do these finite time experiments and still extract out these equilibrium properties. And this is used. It's used a bit in these single molecule experiments, but it's also used a lot in computation. When you're doing, again, I was thinking about simulations of drugs binding to proteins. For example, there was a whole COVID moonshot project where they a publicly funded thing to try to rapidly develop an inhibitor of one of the proteins in the virus. And they used folding at home to do massive scale calculations. And the way they're actually doing the free energy calculations there, they're actually doing these finite time switches and fundamentally using this bit of physics to extract out those how strongly those potential drugs bind to the protein.
Could you go a little bit more into the specifics of that? Like, what do you mean by finite time and what folded at home is? Maybe I don't know if our.
Oh, sure. So folding at home. Folding at home was a project from Vijay Pandey originally at Stanford, going back probably 20 years at this point. So the idea is they wanted to simulate proteins in a time when computer is scarce and expensive. And so they enlisted, they got everybody to donate their spare GPU cycles. So it's a massively distributed computation where people at home can use their GPUs on their idling game system to help with the biology. And when the so this project's been going on for a while. When the coronavirus hit and they refocused on the coronavirus, they got a huge spike in donations of time, and it was by far the biggest supercomputer on the planet. I'm not sure what the current status is, but it was massive. It was amazing because everybody just wants to help, right? So the other part was the finite time. So, in anything like this, when I'm thinking about pushing the piston in traditional thermodynamics, when the way thermodynamics is set up, we're thinking about transformations which are quasi-static, infinitely slow, essentially. That's where we get the Carnot limit, the Carnot limit where we have perfect efficiency of our heat engines. But the problem, so that's a very slow process where I push the piston in really slowly and everything can stay very close to equilibrium. And of course, the problem with that is real life is not in equilibrium. So when we say finite time, we're thinking about when we push these pistons in at a finite rate and therefore inevitably push the system away from equilibrium. And that's where these fluctuation relations still hold. Maybe Jackson, I think you've had your hand up for a while.
Yeah, so it was up and down, and then I had to leave due to computer issues. But I was wondering if I could hear, or we could hear more about your work in quantum computing. Is it like Is it similar to this work, just sort of applied to quantum computing algorithms, or is
No, I'm actually
different?
doing quite different stuff. Although people, strangely enough, have taken this and applied it to quantum computing algorithms. There was a paper just out a few weeks ago, which is kind of interesting. No, I'm been thinking a lot about how do we program these near-term quantum computers is sort of an issue that we don't really know how to tackle. A lot of quantum computing science for a long time was very paper and pencil based because there weren't any quantum computers, so it all relied on what you could prove analytically. Whereas we're coming into this era as these quantum computers come online, we can be somewhat more empirical and just try things. Much more like actual computer science of classical computers. There's lots of theoretical stuff, but in practice, there's a lot of empirical stuff. I mean, just something like sorting. You'll learn about quicksort or whatever in class, but if you go look at what Python, for example, its sorting algorithm is, it's something way more complicated with a lot of heuristics in it. So the quantum computing is coming in that same way. So I've been working on particularly, things we might conceivably be able to implement on these near-term machines when we only have a few noisy qubits, and maybe we can demonstrate some. Still too early to demonstrate like practical superiority over classical computers, but it's about trying to make sure we can run some useful algorithms on these near-term machines and try to see empirically how well things work as the machines develop.
Cool, thank you.
So on these near-term devices, where do you think the kind of early applications of quantum computing will come in, or like early algorithms that will beat out classical devices? What is your kind of
well, that's the million-dollar question, or billion-dollar question, perhaps. It's really totally unclear right now. I mean, what do we know will work? Well, we know we could break RSA encryption, and that's the suicide application, because as soon as you can do that, everyone's going. Well, before you can do that, everyone's going to move their encryption to some quantum secure encryption. So you can't ever make any money out of that by breaking over these Bitcoin hashes. So yeah, it's hard to say. It could be quantum chemistry, because chemistry is fundamentally quantum. You could get an early advantage doing quantum chemistry calculations on the quantum computers. That's actually also very tricky because the quantum chemists using classical computers have got very good at that with a lot of heuristic approximations. So it's actually so although it looks natural, there's actually quite a high threshold to get over to be better than the classical computers. And then people are looking at a lot of combinatorial optimization problems. There's mostly, I think, because it's a fairly straightforward to implement those on the quantum computer. We don't know yet whether they're actually going to show a practical speed up. Again, it's in a way, it's a really early, interesting time because we really don't know what that killer app is going to be. And that's why, it's good to be at this frontier. But to keep one's perspective open as we try to figure out what the right thing is.
Yeah, I wanted to ask a question going back to, I guess, sort of maybe the biographical portion. So you mentioned that Chris Jasinski had this result and it was very controversial initially, and then you hopped in and you guys were sort of the only people working on it. I just wanted to ask, was this scary? Was this exciting? What was that like? Would you recommend that other people try things like this? Or?
Yes. Look, science is a big, field. And there's lots of scientists out there. And if you want to make any progress, the best thing to do is to find some nook where nobody else is. So actually, let me take that back. You either want to be on the, bleeding edge. Yeah, you want to be on the bleeding edge. You don't want to be on the trailing edge. A lot of people just end up following on the trailing edge. I mean, there's good stuff to be done on the trailing edge, but a lot of it ends up being me too, right? And so I think if you want to make, particularly as, a young student, grad student, inevitably you can't master more than a tiny little nook. So try to find a nook that nobody else is working on. Now, I was lucky in the fact that the nook that I was working on turned out to be really important, but that was not, immediately apparent. I thought it was neat, but it's only in hindsight that it's like it really became apparent that no, this really is sort of a generalization of the second law. Did that answer the whole question?
Yeah, I think so. Thank you.
But yeah, no, it was more exciting than scary. It was just absorbing.
Mm-hmm.
So something that you mentioned was that the differences between or that in certain startups, you could imagine doing research that is of similar quality to academic research or something.
Yeah.
What do you think? What do you think the characteristic for these kinds of startups is? Like, if you're looking for a job in this kind of direction, and also, how is it different day to day, maybe?
Yeah, it's if you look at it, it's where there's a talent shortage. So all the big companies want their really good machine learners, and so in order to attract that talent, they've had to offer them the ability to continue to publish papers, for example, right? So I think that's the characteristic. It's where there's it's a very highly it's a cutting edge research field where there's companies that desperately need talent. So they then there's leverage. Right. So going into companies was one of my concerns was always that you don't want to disappear, right? What seems to happen to a lot of people, they go into industry and they're probably working on really cool stuff, but they're not publishing any papers. And so from an academic point of view, they just it doesn't register, right? So the difference is you're looking for companies that are willing to or want you to continue to publish results appropriately. Obviously, there's always some stuff needs to be private to the company, but appropriately the results going out there. And again, I think the really pioneers in the last few years has been the machine learning world. But I think it's spreading.
Do you I don't remember if you said you worked on machine learning stuff, but in this capacity with sorry, go ahead.
A little bit, but it's not like a major focus. But I've certainly done a little bit on machine learning.
I see. Is this
particularly? Sorry, go on.
Is it because of the StatMech kind of angle that's involved, or maybe other directions?
Well, no, I think it's fascinating in and of itself. When the the modern neural network started working a few years ago, we were running a seminar at Berkeley at the time, which was what do we call it? Sort of an intersection machine learning and StatMech. And so it was really interesting to see the field blossom because neural networks have been around forever, and the training them has been around forever. What happened was the GPUs got good enough and fast enough, the data sets got good enough that suddenly they started working. So that's been fascinating to watch. And I've been on the physics side, I've been quite interested in the issues of learning at this very microscopic level. Because at some level, computation is just moving information around, and information is physical. And erasing a bit, for example, has an entropic cost, an energetic cost. And so when you go down to very small systems, you have this the thermodynamics comes in again to the computation. And another related field that sort of I've been looking into over the years is very low dissipation computing. So computing that's operating way down at the Landau limit. So our current computers, I forget, they're inefficient by several orders of magnitude. But if you could get down, if you reduce the energy cost per operation by 2 or 3 orders of magnitude, you start getting into the realm where the thermodynamics matters. And that means, again, because you have these fluctuations, your computer can no longer be a deterministic clockwork-like mechanism. We think of the computation in our computers as like there's a clock, it just moves forward. And that moving forward, that's breaking time symmetry. And the fact that there's very few errors, that requires energy too. So if you want to make a very, very low dissipation computer, like orders of magnitude better than what we currently have, you have to work around the stochastic nature of it. You'll inevitably get some errors. You'll inevitably not move forward in a clockwork manner. So that's a technology that's still many years out, but will, you project out, it's going to be relevant in sort of 10 or 20 years.
Isn't there a way of turning any function into a function that you can kind of compute like reversibly or something like that?
So, yes, absolutely. Reversible computing. Right. So the trick is that the cost of the computation actually comes from the information you have to erase. So the trick, which Landau and Bennett came up with, was reversible computing. So the idea is, as you said, you turn the computation into a reversible function, which means that you have to have a bunch of garbage bits moving along with your computation. At the end of the computation, you copy the result, and that has some energetic cost associated with it. But then you reverse the whole computation, and you go all the way back. That erases all the garbage bits. And so the net upshot is the entropic cost is not the number of, the energetic cost is associated with the size of the answer and not the number of steps. However, where this gets really interesting is that that's reversible computing. So that's like, again, the Carnot limit. So it applies when you go infinitely slow. In any real computation, we actually want to get the answer today. So there's this trade-off between how fast you go, how much energy you put in, and how many errors you get. And so again, as soon as you get into that, once you're away from that finite time limit, all this non-equilibrium thermodynamics comes up and kicks you. So yeah, reversible computer, another technology that's going to be important at some point as we try to reduce energy of computation down. But we still hit these same thermodynamic constraints.
This might be a dumb question, but
there are no dumb questions. There are many inquisitive idiots.
Okay. If you do, isn't quantum computation like inherently reversible in some sense?
It is, absolutely, yeah.
So how I'm kind of trying to understand how these technologies are different at what exactly dissipationless computing is as opposed to quantum.
Well, okay, so the in the quantum computer, the qubits have to be completely isolated, and the computation you're doing, because it's quantum mechanics, has to be reversible. Now, the overall thermodynamic cost of that is quite high because there's a lot of error correction going on. Error correction is always costing you something thermodynamically. And also, they're sitting inside of these refrigerators. And so there's a big energy cost associated with keeping all these qubits very cold. So it's true. Now, quantum computers can beat classical computers on the energy scale as well, because you can get so much computation out per operation on the things that quantum computers are good at. So these are complementary technologies that quantum computers, for the things that quantum mechanics is better at, which is a subset of problems that we're not quite sure what that subset is, certainly includes factoring RSA, then because you can get so much computation out, they'll be more energetically efficient too. But still, we'll always have lots of classical computing, and we would like to make that super efficient too. So again, there is an overlap in techniques, as you said. You've got to have the reversible computing in either sense to really drive the energy cost way down.
Minchell, go ahead.
Oh, yeah, Dr. Crooks, I have a question about the physics part of the colloquium. So when you described about the average of the non-equilibrium system for exponential of beta, minus beta, W, it's just can be computed by the difference in the equilibrium system. So
difference.
Oh, a difference, exponential of the difference of the free energy.
Oh, the free energy, yes. It equals the exponential of the difference of the free energy, yes. Of the equilibrium systems.
So for me, like I thought it's quite unintuitive that the like characteristic of the arbitrary non-equilibrium like protocol is expressed by the equilibrium quantities.
Oh yeah, no. Yeah, it is. So here's the trick. So what in the Krzyzewski setup, right? What we're thinking about a system that starts at equilibrium. Then we drive it with some protocol, and we drive it at a finite rate, and it pops off of equilibrium, right? Now we do a certain amount of work on the system while we do that, which we can measure. Now, conceptually, we can stop doing anything to the system and just leave it at a fixed control parameter. And then it will relax back to equilibrium. And that's the free energy difference you get. It's this equilibrium, it's the difference in free energy between the initial equilibrium system and the equilibrium system in infinite time that you eventually relax back to. But because it features the work that we do on the system stops at the point where we stop driving the system. So yeah, so at the end of the protocol, you're in some arbitrary, who knows, non-equilibrium ensemble. But then what drops out is the free energy of the equilibrium ensemble you would relax to.
Well, I thought like the non-conservative forces or those kind of things can affect the non-equilibrium system, but still like all those kind of things are incorporated in the work that we are exerting on the system. Or I just wonder how we can consider those kind of like friction or those kind of like path-dependent like components of the non-equilibrium system.
So there's sort of different ways about thinking about how to drive a system out of equilibrium. I like this kind of way where I think about what I'm doing. I'm driving the system by changing the Hamiltonian, essentially. Now, there's also, you know, as you say, there's other ways about thinking about it. You add some non-conservative force, or you have, say you have two heat baths at different temperatures that are coupled to the system at different places. And so all of this kind of stuff generalizes up, but there are other, you know, things you have to worry about. Again, as long as you have to make sure you have this right symmetry. So the basic idea is there. I'm just simplifying to this this case here, where I don't have no non-conservative forces in this particular setup. But that kind of thing, it all works, and other people like to think about it that way, and it's all sort of part of the same picture. I'm just overly simplifying. Vivek.
Hi, Gavin. I had a couple questions. One would be on the physics side, and one would be regarding quantum computation. So you mentioned that when we have a reversible quantum computer, what we do is at the end, we just copy over the answer.
No, that's classical computer.
So
quantum computer, you can't copy information in the quantum world.
Yep. So how do you get before you reverse the computation, how do you get the answer?
In the classical. So this is what we do in the classical world in order to make sure the information, by reversing the computation, we reverse the amount of work we had to put into the system so we could recover any energy we had to put in. Can't do that with the quantum, because at the end of the calculation of the quantum, you have to measure the system. And that's irreversible. And so there's an inevitable thermodynamic cost associated with that.
I see. Well, so my second question is, and this has more to do with like definitions, but I'll just put it out. People say that the total entropy of the universe can only increase, right? Now there's a fundamental problem to this statement, and that is, if you take the entire universe, and if you knew the complete state of the universe at any point, using the laws of physics, you'd be able to trace out the state of the universe at any future time, or even any past moment. And you'd know you'd have perfect information about all the microstates. So in that situation, you're not introducing any disorder. So it's not that the entropy of the universe is increasing. So this is you get into really interesting, fascinating philosophical conundrums. And there's a couple of philosophers
who actually I like and do useful work, which I always found quite surprising. Because thinking about time and entropy and the scale of the whole universe is really tricky. What's their name? Hugh Price and David Albert, the two philosophers who've written great books. David Albert is the one who came up with the phrase past hypothesis. So what happens is, I mean, you can take a toy model, like a cellular automata with deterministic dynamics, like one of these lattice gases. And you still get essentially what looks like entropy increasing. So that's a closed, deterministic, reversible system. And what's actually going on is that, yes, in principle, if I had access to the whole system, I could reverse everything, I could access everything, I could compress the information. That assumes you have one, access to the whole system, and two, basically unbounded computational resources. What actually happens is that the information, the entropy, is lost up in the higher order correlations. And you really would have to be able to access the whole system and every detail of the system. And if you only ever see a part of the system at a time, you could never, rediscover those correlations. Now, making that story in a way that makes everyone happy and that doesn't run into these weird situations that you're talking about, like what really is the right way to think about the whole universe, is a fascinating thing and really tricky, which is why I say the philosophers actually end up being really useful here.
I see, but like I think it's imprecise to make the statement that the entropy of the entire universe would increase in a practical sense. Yes, you could say that.
No, I think that's absolutely correct. It does. It's but you have to. There's always some part where you have to, in some sense, you are hiding information.
But if you are hiding information, you're creating that out of thin air, and well, there is no free lunch. So where's that coming from?
Where's that coming from? Where's what coming?
Yeah,
from?
well,
the free lunch is coming from the fact that the early universe is this very localized thing with no long range correlations and very low entropy. So that means there's lots of room for us to go hide information in.
I mean, if it's quantum mechanical, you never, like, the full state of the universe doesn't really change. It's every operation is unitary. So you're. But
then, we're talking about the full universe, and not all of the universe can see each other at the same time, and it all gets really iffy. Again, it's like, I understand the kind of issue you're bringing up here, but the resolution of this is something that people have banged their heads against for many years. Well, and again, my practical point of view is to dodge it for most part.
Exactly.
In my working life, this is the fun thing to have conversations over beers about.
Exactly. So that's what I'm trying to get at here.
And over beers we could have a long conversation about how I think the right way to resolve these issues are, but I'm not certain about the right way to resolve these issues.
No,
I think it really is a deep problem of physics and the origin of the universe, and even just philosophy about what we mean by entropy and information and arrow time.
Thanks.
Yeah. Connor.
Hi. So back to like you're talking about the reversible, like classical computing. I guess at that point, is there any like inherent difference between like reversible classical computing and like quantum computing, where you treat the qubit as like just a bit essentially? Because it seems like there's like error correcting on both, and like
then it's essentially the same thing. It's the same thing. You still, in quantum computing, the calculation always has to be reversible. So, up until the point you do the measurement.
All right, thank you.
So we've taken 15 minutes more out of your life. So we apologize for this.
I hope this was fun.
We had a lot of fun. So do you have any like final words of wisdom? Maybe not final, but final for this Chilloquium. Like closing thoughts.
Closing thoughts. the path through science is always winding. And you just have to sort of follow your intuition about what's an interesting problem and what's interesting to you.
Great advice. With that, thank you everybody for coming and sticking around and asking questions. We'll see you guys next week. We are unfortunately done with the low energy physics or comparatively low energy physics for the time being, which pains me. But we have some very exciting people talking about astrophysics and particle physics for the next 2 weeks. So stay tuned for emails, and looking forward to seeing you guys.